Okay, so I'm going to be doing Spring 2018 Midterm 1C, question 3. So I drew out my line charge, and I marked my point of interest, which is x, 0, 0. This is my x-axis. This is my z-axis. And lambda is given, which equals negative alpha z. And lambda is defined as a charge per length. So since there's a negative in front of our charge density given as negative alpha z, or as negative alpha, so our charge density is defined as negative alpha z. Because it is negative, this tells us that negative charges will be above the x-axis, while positive charges will be below the x-axis. Now we need to find the potential at a distance x away from the center. So our electric potential equation, let me move this up. Electric potential equation is V equals KQ over R. Okay, so if we took, say, this charge and found the potential at this point, at this distance r away, and we found the potential of this charge at a distance r2 away, we would see that if the distance is exactly the same, and the charges have the same value except one is negative and the other one's positive, then potential would just add up to be 0. So for instance, KQ1 over R1 plus KQ2 over R2. This equals K, let's just say the value is -2 times 10 to the -9 over 0.10 plus K 2 times 10 to the -9 over 0.10. This would just equal 0. So because of the symmetry of this problem, our potential adds up to 0. And if this problem was, defined lambda as 1, then it would just be positive charges instead, and there would be a potential. It wouldn't be 0. And why we could say that potential is 0 in this case for this problem, but electric field is not 0 is because potential is a scalar quantity, so there's magnitude and no direction. But the electric field with this problem, there's direction. So we'll see later on. I'll show how certain directions would equal to 0, but there would be a value for other directions because its electric field is a vector quantity. So I'll explain that now. So let's just write it out that V equals 0 because of symmetry. I'm going to move back to the diagram because we're going to find the electric field of this line charge at a distance x away from the center. So zoom in. So let's say we're going to take a tiny element of our, we're going to pick a tiny element of our line charge. So we're going to call this tiny dq. And for a negative charge, the electric field radiates inwards towards negative charge, while for the positive charge, the electric field radiates outwards. With these so electric field is a vector quantity, so it has direction. So this field line has an x and y component. That's for this, and then for this line. So we see that these are both equal and opposite, so they would just cancel out, while these would add up in the z direction, the positive z direction. So let's write out our point charge equation. Our point charge equation is electric field is equal to kq over r squared, r hat. However, for our tiny element, the equation is going to be written as dE equals k dq, because tiny is dq, over r squared. Just define this as r, and this distance is x, and then this is our z distance, and then so dq is equal to, so dq is the amount of charge in, dq is the amount of charge in the length of this is dz. So that would be lambda times dy. So this is the amount of charge in length, dz. The amount of charge in length dz. And then our lambda is given as negative alpha z. Actually, I don't need to put this negative here because I already took account the negative when I said that the negative charges are represented as the I took account the negative when I defined that the negative charges will be above the x-axis, and the positive charges will be below the x-axis. So this will just be a positive because I took account of it already here. So it should be positive. And then so that's dE, but our electric field has components that add into z direction only. So dE z equals dE sine theta. Sine theta because I'll show you here. So this, the vector here and with the x-axis is defined as theta. That's theta. So then that's theta. This would also be theta. And since this is our hypotenuse, and this is our adjacent side, that would be cosine. But since this is opposite in hypotenuse, it would be sine. So that's why it's sine theta. Opposite hypotenuse in this direction. Okay. Okay, going back to here, substitute in our values here now. So it'd be k alpha z dz sine theta. So do some tricks. So sine theta is opposite over hypotenuse. So my opposite, looking at this triangle, my opposite is z, and my hypotenuse is r. So z over r. This is r squared. Oh. So then k alpha z squared dz over r cubed. And that's just one of our tiny. So that's one of our tiny pieces. So we're going to integrate the tiny pieces to get the total electric field of this line charge on that point of interest. So our electric field is equal to k alpha L over 2 to negative L over 2 z squared dz over r cubed. So we're going to solve for that. Here. Okay. I'm going to redraw this triangle right here for reference. Okay, so z squared dz over r cubed. We're going to do some trig. So tangent theta is equal to opposite over adjacent. So z over x. Z equals x tangent theta. dz equals x secant squared theta d theta. So that's going to be substituted in for z squared and then dz. Then for r cubed, we're going to have cosine theta is equal to adjacent over hypotenuse, so x over r, and that's r equals x secant theta. Okay, so we're just going to that into, substitute our value that we got. This cancels out. Oh, no, that we're left with 1 actually. this cancels out. And then this is canceled out. So we're left with tangent squared theta is the same as sine squared theta over cosine squared theta. And then 1 over secant is the same as cosine theta. So that cancels out. This is another trig identity is sine squared theta is equal to 1 minus cosine squared theta. So that becomes 1 over cosine theta, which is just secant theta. And then cosine squared theta over cosine theta is just cosine theta, d theta. Integrating, we'll get, well, taking the derivative. So ln will become ln secant theta plus tangent theta minus sine theta. And with our problem, it's finite, so we're dealing with length. So this has to be substituted using trig sub in terms of length. So that we go from L over 2 to negative L over 2. Because of the symmetry of this problem, we could actually just do it's the same as going from L over 2 to 0, and just because our result's going to be the same, we should just put a 2 in front of the answer. So another piece of paper. Okay, so we're gonna, oh, this is actually, yeah, that's right. Okay. Okay. Now, integrating that, we'll get ln, our r in this case is equal to z squared plus x squared square root. So x squared plus z squared. Z is going, we're integrating, so it's going to be L squared over 4. And then that z is going to be L over 2. And then x. And then L over 2. And then r, same. Okay. And then our electric field is equal to, the direction is going to be in the z-hat direction. And then K alpha ln just writing all this over again. And then 2 because we only integrated from L over 2 to 0. We only did half, so another half would be the same, just adding it, so it would just be 2. We would get the same answer if we did it from L over 2 to 0, L over 2 to negative L over 2, so it's the same, so we would get the same, this would be adding to this, so it would just be 2 of this, so it's going to just be the total electric field of the line charge. The total electric field of the line charge at this point of interest is equal to this. Now apply this result to find the electric field of a square plate of length L by L at a distance x away from the center. Surface charge density of the plate is S equals negative BR. Set up the integral in details, but do not carry out the integration. Okay, so in part A, we found the electric field of a line. We can apply this to the plate because the plate is essentially made up of infinite lines. So we're going to have our tiny, for this would be an infinite line. Now, in A, our total charge for the infinite line was equal to lambda L. To be able to apply this to the plate, the charge has to be the same. So let's write this out. Lambda L equal to sigma because lambda was from 1D, now we're in 2D, so that involves area, sigma, charge per area. L, dy, L, because it's the length of the line is a constant, from here to here, and then dy because it's varying. So how we're going to integrate to get the electric field. And then we know lambda is equal to alpha z, and then sigma is given as negative beta z, and then L dy. Doing some cancellation, we're just going to get alpha beta dy. Okay. Now we need to find the direction. So from our result in part A, the electric field added in the z direction. So when we apply this to the plate and our point of interest, which is x, 0, 0, the electric field would also be adding in the x direction. And same if we had another line charge over here, also be adding in the x direction, z direction, adding in the z direction. Another thing that would also be changing, so the line that comes from our line charge, the point of interest, we're going to name it S instead of X, which was here, because this was constant. But now our line charges are moving away, so our line charges change, so the distance is going to change. So we're naming that variable S. Okay, and now taking our result from A, we're going to substitute the alpha for beta dy, and then X is going to be substituted for S, and then we'll go from there. To get D E is equal to z hat, the direction where the electric fields add, 2k beta dy ln, substitute our x for s, so you can see that our result, how am I going to do this? So here we had z hat 2k alpha, now it's this, z hat 2k beta dy, and then we changed the x's here, I'll change to s's. And there's one more step. So now we're going to set up the integral. We're integrate it. So it'll be z hat 2k beta going from L over 2 to negative L over 2. So if the length here is defined as L by L, this side we'll just say is L over 2, and this side is negative L over 2. They both add to make L. So then we're going to replace s squared by x squared plus y squared. S is the hypotenuse. S is the hypotenuse, so it'll be y squared plus x squared. So x squared plus y squared plus L squared over 4 plus L over 2 over x squared plus y squared. So maybe I change here to x squared plus y squared and then x squared plus y squared. And that is the integral for the, to find, which would be the electric field of a square plane at a distance x away